Let's take a look at the concept of continuity of a function. What the continuity of a function refers to is the connectedness of the graph to itself. So let's illustrate that by taking a look at this portion of the graph right here. If I trace along this graph with my pen or pencil, do I have to lift up my pen or pencil to continue tracing? And the answer is no. These points are all connected to each other, and therefore we say that the graph is continuous at all of these points. Now notice as I get to this point right here, there's a hole in the graph, and that basically means that a single point has been removed from this segment of the graph right here, which means there's a break. So now as I trace along here, yes, I have to stop, jump over, and continue on down the graph. And so we have a hole discontinuity, which is also called a point discontinuity or a removable discontinuity at x equals -3. As I continue along, right here I get up to x equals -1, and my y value suddenly jumps down to this part of the graph as I continue on to the right of -1. So now I continue along here. This part of the graph is continuous. Everything's connected. I don't have to lift up my pen or pencil. I continue on, but I see that this graph is now going all the way out towards infinity. Okay, it's never going to stop going up the closer I get to x equals 2. And that's what this dotted line indicates right here. We have a vertical asymptote. And so this is another type of discontinuity called an infinite discontinuity. As I get to the right of x equals 2, I'll be down on this portion of the graph right here, and as I continue along, we're continuous along this way. How do I know that it's continuous? Let's look at this point right here. When x equals to -4, I actually have a y value. It happens to be y equals 4 right here. So when x equals -4, y equals 4, and in function notation we write it this way. We would say that -4 is my x value, my input. When I put that into my function f, it gives me a y value of 4. And I can see that as I move along the graph towards x equals -4, my graph is going to approach a y value of 4, no matter if I approach from the left or from the right. And so everything is coming together at a point. When it gets to that point, there's a point there to connect the two pieces together. Everybody's happy. That's what we call a continuous function at that point. So let's look at this a little bit more formally. We've already decided that our function value does exist at that point. I'm going to turn this switch on here, and what this is going to do is give me a slider here that is going to allow me to move an x value closer and closer to -4 in this case from the left. And when I turn this one on here, I'll do the same from the right. But what that's going to allow me to do then is to look at the y value and see what it's doing as x is approaching -4. So that's going to tell me about whether this graph is approaching my y value here. So I'm going to slide this slider here, and I want you to watch this x value here. So we can see as I slide here, my x value is approaching -4 from the left. And also notice then that the y value that's with this particular x value here is approaching +4 as I get closer and closer to x equals -4. And so we can read that result here as x approaches -4 from the left side, y approaches +4. I can do the same thing on the right side. Here's my x value that's going to approach -4 now from the right side. As that happens, my y value, as you'll see, will approach 4 as well. So I'm going to just start sliding this over, and we see that the y value is going to approach 4. And so we said that this point was a point of continuity. In other words, the function is continuous at this point in the graph. How do we know that? Well, we know that because there's a function value there. Its value is y equals 4. As we approached -4 from the left side and the right side, our y values also approached 4. And that's indicated by this limit notation down here. Now, a limit is a concept that basically says as x gets really close to some number, negative 4 in this case, and in this case we're looking at getting close to negative 4 on the left side of negative 4. Okay, what is my function doing? Well, it's approaching 4. So as x gets close to negative 4 on the left side, my function is approaching 4. As x gets close to negative 4 on the right side of negative 4, my function is approaching 4 as well. Okay, and so since these two are the same, we say that the limit of the function as x approaches negative 4 is equal to 4. And that's what this notation means right here. Now, the fact that these two things are the same means that this limit is going to exist. Okay, it equals 4 coming from both sides, and so my limit is 4. Also, my limit is 4 and my function value is 4 at that point. These two things together really are the definition of continuity. Does the limit exist? Does the point exist? And do they have the same y values? In this case, the answer is yes, and so the function is continuous at that point. So we'll go ahead and capture that in the table over here. We have, as x approaches negative 4 from the left, y is approaching 4. As x is approaching negative 4 from the right, y is also approaching 4. And when x is equal to negative 4, y is equal to 4. That is what makes the function continuous. Let's go ahead and move over to the hole in the graph right here at x equals negative 3. Okay, and what we see here is that when x equals negative 3, my y value is undefined. And that makes sense because we know that we have a hole in the graph. When x is negative 3, my function says, I don't know what to tell you, there's no y value to give to you. So the y value is undefined. Okay, so right away we know that if there's no y value there, then the graph can certainly not be continuous because I would have to skip over that if I were tracing along the graph. But let's take a look at what happens on either side as we did before. On the left side, as my x value approaches negative 3 from the left, my y value is approaching 3. Now again, approaching just means I'm getting very, very, very close to negative 3 on one side or the other. It does not mean I'm equaling negative 3, because I know that if I equal negative 3, I don't have a y value. But the closer I get to negative 3 on the left, the closer my y value gets to 3. Same thing on the right. As I get closer to negative 3 from the right in x, my y value gets closer to y equals 3. And so what we see here is that our graph is approaching the same point from both sides, but there's no point existing once we get to there. And that's what is the hole in the graph. So again, in the table over here, now we can see that as we had with the continuous point, our graph is approaching a y value from both sides, but when we get to that particular x value, the y value does not exist. It's undefined. And so a hole, also called a point or removable discontinuity, is really defined by this behavior that you see right here. All right, let's take a look at x equals negative 1. This is our jump discontinuity, and let's see if we can figure out what's going on here. So at x equals negative 1, I put that into my function, and the function says, oh, y value is equal to 1. When x equals negative 1, my y value is equal to 1. But let's see what happens from the two sides, and I think it's pretty clear from looking at the graph, but we'll go ahead and walk through this. As x approaches negative 1 from the left, y approaches 1. So watch what happens to the y value as x approaches negative 1 from the left. My y value is approaching positive 1. Now, on the right side, as x approaches negative 1 from the right, my y value is going to be way down there at negative 3. And the reason is because on this side of negative 1, my x values correspond to y values along this part of the graph, which, as you see, is heading down towards negative 3 as I move closer from the right. So as I slide over this way, my x value is approaching negative 1. My y value is way down there at negative 3. And so what we can see, turn those back on. What we can see here in this case is that my limit on the left side as x approaches negative 1 from the left is 1, but the limit as x approaches negative 1 from the right is negative 3. Therefore, the limit does not exist. Because these two things are not equal, there's no way that I can say that the limit is one thing or the other. It can't be both of these things, so it's basically neither. Okay, so the limit doesn't exist. Now my function value exists, perfectly fine function value, but this tells me that my function has a jump discontinuity in it. So again, we'll go ahead and update the table over here. My jump discontinuity basically says that as I approach my x value from both sides, I get different y values here. Okay, different y values, 1 from one side, -3 from the other side. Doesn't matter that I have a defined value here. In fact, even if this were undefined, this would still be a jump because I'm heading towards two different y values from the two different sides. Our last type of discontinuity is the infinite discontinuity, which is basically the vertical asymptote here. On the left of x equals -2, we see that as I approach, positive 2, as I approach positive 2 from the left side, my y value is climbing and climbing and climbing, and the closer I get to positive 2 from the left side, the higher the y value gets, and so basically it's going off to infinity. When x equals 2, y equals infinity, even though this is not very good notation because we can't equal infinity, but the idea is that the graph has grown infinitely large, and that's the same idea as what's indicated down here. From the right side, okay, here's my value here that I'm going to approach 2 from the right side. We can see that the y value is heading down to -2. And so as x approaches 2 from the right, y is approaching -2. That same concept on both of these sides is indicated with the limit notation here. Once again, the limits are different on the two sides, but notice that one of them is infinite. And because it involves infinity, we don't want to call this a jump. We're actually calling this an infinite discontinuity. And it's really because an asymptote is really a completely different animal than a jump here. This is just changing finite y values. This is actually going to infinity. So it's really a different thing altogether. Now, this could be infinity. This could be negative infinity. I could have positive or negative infinity or both on both sides. As long as there's infinity in one place or the other, this is called an infinite discontinuity. And that's all captured in the table down here. We have our y value going to infinity on this side. So again, this could be positive or negative infinity. This could be positive or negative infinity, one or both sides. That would still make this an infinite discontinuity. So let's just go ahead real quick and review. A continuous function occurs when our limit exists because our two one-sided behaviors are the same. In other words, we're approaching the same y value from both sides, and it's equal to the same y value at that point. A whole discontinuity occurs when the one-sided behavior gives us a limit that exists. In other words, it's going to the same y value, but either the y value is undefined, as we have in this case, or possibly the y value could be defined to be a different value. So basically, this limit is not equal to this. A jump discontinuity, we're going to two different y values here, making this limit non-existent. Doesn't really matter what's happening here at x. We could be x at the x value. We could have a defined value, or maybe we might not. And again, the infinite limit we just discussed. So that's continuity, and thank you very much.